Greetings all present here. Honorable Chief Guest, Mr. Samuel Jigme Harrison, Senior IC Design Engineer Limited. Respected Ma'am, Dr. Deepa Joss, Professor and Head Research. It's my immense pleasure to extend a very warm welcome to all of you present here on behalf of KCG College of Technology. We welcome you all to the 4th series of International Research webinar on the topic Physical Design in the Semiconductor Industry. For decades, the semiconductor industry has been defined by the ability to innovate. Each time they faced with seemingly insurmountable technological challenges, they have invented innovative approaches and methods to solve them. And in doing so, they have helped to transform how the world works, plays, learns, and connects. From computing devices to smart appliances, automotive to healthcare equipment, data centers to satellites in space, semiconductors are driving force behind every electronic device and every innovation. The VLSI, very large-scale integration, is a process of embedding or integrating hundreds and thousands of transistors into a single silicon semiconductor microchip. VLSI technology's conception dates back to the late 1970s when advanced level processors, microchips were also in their development stages. Recent developments in VLSI technologies leads to integration of millions of transistors on a single chip. Henceforth, we take this opportunity to extend our knowledge and get benefited. Now, I welcome Dr. Deepa Joss, Professor and Head Research, to introduce the Chief Guest.
Warm welcome to all the participants of this event to take time and join for the session. I welcome our resource person, Mr. Samuel Harrison, sir, to take time and spend with us to share a few insights into the research trends and give the industry expertise and your industry expertise that you have gained over the past 15 years to all the students and the faculty members. Let me introduce a speaker. Mr. Samuel, sir, has completed his engineering in electronics and communication, and he has done his master's in science, specializing in integrated circuit design from Nanyang Technological University, Singapore, and Technical University of Munich, Germany in 2010. He also holds a master's degree in business administration from Anglia Ruskin University, UK. So welcome to the session. Samuel sir has started his career with Avago Technology Singapore in 2010 as an entry-level IC design engineer, and sir has got promoted as a senior ASIC design engineer in 2014, and the company was renamed as Broadcom Limited Singapore in 2016. Samuel sir is currently working with ST Microelectronics Asia Pacific PT Limited Singapore since 2017 as a senior digital IC design engineer. Sir is having more than 15 years of experience in VLSI, specializing in physical design implementation. He received a Technical Merit Award, Best Paper Award in SNUT Penang conference conducted by Synopsys for presenting a paper titled A Novel Approach in Security Implementation and Clock Tree Synthesis Using ICC2. He has also published an article titled Importance of Security in IC Design by the Singapore Semiconductor Industry Association, SSIA, in their technical magazine. Sir has been a keynote speaker and resource person in various international conferences and seminars. Sir is a member of various technical societies, including the Institution of Engineers of Singapore, and the Singapore Semiconductor Industry Association, the IEEE Computer Society, and the IEEE Solid State Circuit Society, and the VLSI Society of India, and many more societies. So we are in fact proud and privileged, our college faculty members, and there are faculty members from across other states of India as well as from Tamil Nadu, and all our students and the faculty are keenly awaiting your session. Over to you, sir.
Thank you, ma'am, for the brief introduction. And once again, thanks to KCG College of Technology for giving me this opportunity. So I especially thank each one of you who have taken time to attend this session today. And let's move on to today's webinar on physical design in the semiconductor industry. Okay, hope you are able to see the screen.
Yes, sir. Yes.
Okay. So before moving on to today's topic, I would like to give a brief introduction about the semiconductor industry in Singapore. The first semiconductor organization was opened in 1968, and Singapore has more than 60 semiconductor companies, which employs around 35,000 people. The semiconductor industry here contributes to 7% of the country's economy. So government takes in more efforts to put in new courses in the universities and give grants to research institutes to come up with new designs in the technologies. So my workplace is ST Microelectronics. This is Europe's largest semiconductor chip maker and one of the world's largest semiconductor companies with its headquarters at Geneva. We serve around 100K customers around the globe with 11 manufacturing sites. So we have more than 46,000 employees worldwide and 18,000 active patents. And Singapore is the Asia Pacific headquarters for ST Microelectronics. So today's topic on physical design. As we all know, in VLSI design, there are two portions. One is the front-end design and the second one is the back-end design. So this is the development cycle of digital IC. So in front-end design, we have circuit representations, schematics using Boolean logics, AND gate, NOR gate. All these schematics have been designed in front-end design, which comprises of VHDL Verilog codings, and the output is a netlist. So from the front-end team, we get this netlist, and physical design is the process which transforms this digital circuit to a physical layout. So the function is the same. Only thing is the circuit connections in the front-end design is been replaced with metal layers. So for example, from register A to B, your connection is through metal layers. You have metal 1, metal 2, metal 3, metal 4 layers in physical design. So these are like geometric shapes, and these metal layers are in different colors. So this will ensure that the function remains the same throughout the circuit. So this is the IC design flow for digital circuits, where you have the system specification, architectural design is from the customer, and then you get the front-end team to work on the functional design, logic design, and circuit designing, and then comes physical design. So physical design is also known as back-end design, and we have partitioning, floor planning, placement, clock tree synthesis, signal routing, timing, closure as steps of physical design. So usually in universities, we will come across this in the 3rd and 4th year. We will have VLSI subjects where we will have exposure to Boolean logics, digital logic design, and we will also have a lab on floor planning, routing, and so on. After physical design is the physical verification part. So we have physical verification and also timing analysis, where we check for setup and hold time, followed by manufacturing of the chip. So once the chip is manufactured, it is given to the packaging team, and the testing is also done on the manufactured chips. So only after packaging and testing is done, the chip is given out to the customer. So this is the flow of IC design. So inputs to physical design are, we have a netlist, library information of the cells in the design, and which are known as .lib, and a technology file for each nanometer. Suppose for 40 nanometer design, we will have a technology file with the manufacturing constraints and the timing constraints. So this technology file is provided to us from the manufacturing company. Either it can be TSMC or whoever is manufacturing this chip. Timing, power, and design constraints are met during this physical design. So these are the 3 areas where main focus is being given to ensure that the chip is working properly. So For physical design, we have two tools in the market. One is Innovus from Cadence, and the other tool is ICC2 from the company called Synopsys. But majority of the IC design houses, they use Innovus, which is user friendly. And now is a short introduction to Innovus. The Innovus implementation system is the physical implementation tool used by majority of the semiconductor companies in the world. So it can handle designs with 5 to 10 million instances. Innovus is very user friendly, and the references and user guides are well explained. So key aspects why we use Innovus is it can handle large designs with efficient turnaround time, because the main concern in physical design in VLSI is the turnaround time for one full cycle. Placement technology is timing, power, and congestion driven. And also we have routing, which is also a step of physical design. Routing is also timing and crosstalk noise driven. And we have unique standard cell placement capacity for high complex floor plan. So the tool is being updated frequently. The engineers who work in Cadence, they use this tool across complex designs, and they try to improve the tool in different versions. So this actually helps the IC design companies in a very great extent to reduce their turnaround time and to make things easy. So this is how an Innovus GUI will look like, where you have the toolbars at top, menu bars, and you have each section for floor planning, power planning, placement, clock tree synthesis, routing. So all the steps of physical design can be performed when you open this Innovus graphic user interface. And you have some small options for opening, saving, selecting, deselecting, drawing a net, moving an instance, or cutting a wire, and so on. And then you have an online help box for you to search for commands, and a layer control bar. So this layer control bar has all the options for you to enable, disable instance, block, standard cells, cover cells, physical cells, blockages, congestion, and also the layers being used in the design. For example, if you have 6 metal layers in the design, you will have VRs for all the 6 layers, and you can enable, disable them. This will help you usually during tracing a net, or during fixing a DRC short spacing violation, or for timing analysis. So this is how a design, an Innovus GUI will look like when you open a design, and you have coordinates of your cursor being displayed at the bottom, and you have a query button. So when you click this query button and you place your cursor in an instance, it will show you the name of the instance and the input output connections of it. And then you have a facility for you to select the net. So when you click a net, your net name will be displayed in bottom. So all these are small features available in the Innovus GUI. So you will have more access to it once you start working using this tool in your university or in your workplace. Okay, so what are the steps in physical design? The main steps in physical design are floor planning and power planning, placement, clock tree synthesis, routing, static timing analysis, and physical verification. So some of you might have come across this in your studies. So today we will have a very in-depth study on each step with some snapshots for you to understand the concepts very clearly. Okay, so first is floor planning. Okay, floor planning is a critical and the first step in physical design. So this is similar to how you consider floor planning of a building or a house by an architect. So the architect has to come up with the size of the building, the area left out for the garden, and also where to place the gate, and how big is each room. So where do you place the rooms? Because you cannot place the kitchen at the entrance of the house. So there are some logics behind floor planning for a house. So the same applies here, where the physical design engineer, he comes up with the size of the floor plan, and to make sure that the floor plan is capable to place itself in the die later during packaging. So he has to take that into account, and then he has to decide where to place the macros. And so in that case, he has to come up with the proper floor plan of placing the macros, the memories, the pads, the analog IPs, and so on. So he has to decide how much channel of space is required between the macros and so on. So what are the goals of a good floor plan? We have to attain minimized chip area, and routability of the design should be possible, and there should be minimal congestion. So only when you have minimal congestion in the design, you are able to get good timing, and also minimum DRC violations. And your floor plan should result in low power consumption, because right now all the designs, the chips coming up in the industry are at low technology nodes because of the shrink between source and drain. So this will result in lots of complications during the design phase in fixing timing and also DRC violations. So we need to ensure that also power is as low as possible. What are the steps in floor planning? First is size of the chip is determined, and then we have IO pin placement, macro placement, creating standard cell rows, and adding routing and placement blockages. So these are some of the steps, the important steps in floor planning. Floor planning can be controlled by two parameters. One is aspect ratio and core utilization. So aspect ratio and core utilization both help in determining the size of the floor plan. So aspect ratio is the width to height ratio of the chip. So width can be related to horizontal routing resources, and height can be related to vertical routing resources. So aspect ratio is number of horizontal routing resources by the number of vertical routing resources available in the chip. So if your aspect ratio is 1, then the block shape will be a square. And if your aspect ratio is greater than 1, then the block shape will be a rectangle with more routing resources in the vertical direction. So your height is greater than your width. Same thing, if your aspect ratio is less than 1, then the block shape will be a rectangle with more routing resources in the horizontal direction. So where your width is greater than your height, and this will help you to determine the size of the floor plan. The second is your core utilization. So in your floor plan, you will have standard cells and macros present and IPs. So you need to find their core utilization. So how much area is the standard cell and the macro taking? So the remaining space is left for routing. So now if you have your core utilization as 0.6, it means like 60% is already used for cell placement and only 40% is left for routing. So if your core utilization increases, then you will have less resources for routing at the later stage, which creates congestion, and you will not be able to route the design. So we need to make sure that the core utilization is always between 0.5 to 0.6, so that we will have more routing resources. During floor plan step, we need to place core rows in the design. So these rows run across the floor plan in the horizontal direction, and these are rows on which the standard cells are being placed. So the height of the standard cell will determine the spacing between the core rows, and alternate rows are flipped to change the row orientation. So this I will explain to you later when we do power planning. Spacing between macros is a must to be taken care of. So we have a minimum spacing which should exist between macros for the pin sites. So each macro will have pins on their side, and we need to make sure that all the pins can be routed later during route step. So the pitch of a pin should correspond to topmost layer when the two macros are placed close to each other. So if you have two macros close to each other and one macro has metal 4 pins and the other macro has metal 5 pins, the pitch should correspond to the metal 5 pins. And as far as possible, open spaces should be avoided in the floor plan. So we need to make sure that the macros are spaced out properly, they are placed properly. And if there is a possibility, we can also abut macros together so that if there is a group of macros belonging to a same group communicating with the same pin or a same logic, then we can group them together, we can abut them together, provided the pins are facing outward. The pin of the macro should always face the logic area. If it faces the boundary of the chip, then we will have long routes during route step. So we can also use a data flow diagram and fly lines as reference. So when you click a macro or an IP, it will show a blue color line known as fly lines. So this will help you to identify which the communicating point of the macro. And also data flow diagram is provided to us from the customer. So we can go through the data flow diagram. We'll have information on which macro communicates with which logic. And so we can, based on the data flow diagram, we will get an idea, a basic idea of how the connections are being done and how we need to place the macros. So we need to make sure that the routing channels between macros is big enough to accommodate the signal routes and power stripes. Macros can also be abutted with the pin sides in the opposite direction. Okay, during floor plan step, we need to take care of blockages, which are placement blockage and routing blockage. So this placement blockage prevents placement of standard cells, buffers, and inverters. So we need to make sure that placement blockage is used in thin spaces between macros. This is mainly to avoid placement of standard cells or buffers in unwanted areas. So when we put this placement blockage in all the thin spaces between macros and small areas throughout the boundary of the chip, we will force the tool to place the macros, the standard cells in the center of the chip. So we need to always ensure that macros and IPs are placed at the boundary of the chip, and we have more space in the center for the standard cells. Routing blockage prevents routing of metal layers in the blocked region. For example, if we have metal 4 power route throughout the design, and in one particular area we plan to put an IP, so we need to have routing blockage over that area. So for that reason, we put a metal 4 routing blockage over that particular area. And now when that metal 4 route is created, the tool will not create routing of metal 4 in that particular region because it is already blocked. So here is a snapshot of how the macros are abutted together, and you can see that they are grouped together. Macros belonging to one group in orange, one group in gray, one group in brown, and one group in dark blue. So this is to just show that macros should be placed at the boundary of the chip, and more space should be given in the center for the logics. And we need to also take care that macros belonging to the same group should be placed together, because you cannot mix macros from this group in orange to this group in blue, which will later result in long routes and unwanted congestion. The second step in physical design is power planning. So what are the goals of power planning? We need to ensure that the power mesh is properly created. So the power mesh means VDD and ground are the main power connections in the chip. So we have we should have VDD and ground power stripes running through the entire chip. So, and we need to ensure that all the power pins of all the IPs and standard cells are properly connected to VDD and ground. So this will help you to meet the IR drop budget. So it will help you to have a low power consumption and low IR drop results. The components of power planning are block ring, core ring, routing of standard cell pins, adding VDD and ground stripes in the core area, connecting pad pins, connecting block pins, and global net connections. So first we have block rings. This block ring is present around each IPs. So we will have VDD and ground rings around each macro, and the core ring is the VDD and ground ring around the boundary of the chip. And we have routing of standard cells. So each standard cell present in the chip will have VDD and ground power pins. So these power pins have to be routed, and we have to add VDD and ground horizontal power stripes, vertical power stripes in the core area. And we need to connect all the pad pins, the block pins, and we need to ensure there is a global net connection of power. Okay, the first one is adding power pads. These pads supply power to the chip. So each floor plan will have a VDD and ground power pad. So this is to ensure that this power pad is connected internally to the vertical and horizontal metal stripes. And when this chip is being placed in a board or a package or some external device, the power from the external device should be connected to this chip. So this power pad acts as a liaison between the internal power of the chip and the external power supply. And block rings, as I mentioned earlier, they are power stripes around the macros. So around each IP or macro, we will have VDD and ground power stripe power block ring. Next is the horizontal and vertical power stripes. So the VDD and ground power stripes run over the entire section of the die. So horizontal wires are known as stripes, vertical wires are trunks. The block rings, the standard cell power rails are connected to power pads through the VDD and ground power stripes. So these power stripes actually use the highest metal layer in the chip. For example, if you have 6 metal layers in the chip, 6th layer will be used for this horizontal and vertical power stripe. The reason is when your metal layer, when you use the highest metal layer, it is the widest and more power, more current will flow through it. So since the metal stripe is wide and you have more current flowing through it, you will have less resistance. The next is the standard cell rail. These rails are used to supply power to the standard cells. The cells are connected to the rails through follow pins. So in Innovus, we have a feature called a route through follow pins. So through that feature, we are able to connect all the standard cells with the standard cell power rails. Now the follow pins are usually in either metal 1 or metal 2. So if we have 6 metal layers in the design, metal 6 will be used for the main VDD and ground power stripe. Metal 1 is used for this follow pin connection. So this metal 1 follow pin connection will be helpful to connect the standard cells with power rails. So the row orientation of alternate standard cell rows is flipped so that the standard cells are connected to both VDD and ground. So for example, if you have a standard cell rail and you have a first row with standard cells. The top of the standard cell will be connected to VDD. Bottom of the standard cell is connected to ground. And the second standard cell rail, if you follow the same pattern with VDD at top and ground at bottom, it will short with the previous row with standard cells, VDD at top and ground at bottom. So every alternate row has to be flipped so that the VDD of the second row is overlapping the VDD of the first row in order to avoid the shorts between VDD and ground. So that is the main reason why we flip alternate rows during standard cell placement. So here we have a snapshot of how power planning is being done. We have VDD and VSS core power rings over the entire die. And then we have power pads. You see this power pad is connected to VDD, this power pad is connected to VSS, and this has following the same procedure. So horizontal power stripes are trunks, whereas vertical power stripes are straps. And here you have rails in yellow color. So these rails are helpful to connect with the standard cells. So this is how the standard cells are being placed and power planning is being done in physical design. Okay, so this is how your design will look like when you open up in Innovus, where you have the chip in between and you have block rings surrounding the chip. You have VDD and ground. The horizontal metal layer is 1, vertical metal layer is 2. So you have VDD and ground power block power ring. And now you have your main VDD and ground power stripe connecting the VDD and ground block ring. And then you have standard cell power rails. The top power rail is connected to ground, bottom rail is connected to VDD, and it is running through the region for standard cell placement. So this is the end of power planning, where you have completed power planning and made sure that all the VDD and ground power pins are properly connected so that there is no hotspot later during IR analysis. The third step is placement. This step is mainly useful for standard cells to be placed. So what are the objectives of good placement? Timing and power, minimum cell density and pin density, routable design, good control over congestion, minimum timing DRCs. So the objectives of all the steps of physical design are almost the same. We ensure that there is less power, timing is met, and there is minimum cell density, the design is routable, there is less congestion. So which means that each step is linked with the other. We need to ensure that floor planning is properly done, followed by power planning, and followed by placement. So if the floor plan is not good, then the subsequent steps of physical design will be a mess. So we need to ensure that floor planning is properly done, power planning is properly done. Power planning should not lead to any shorts or spacing violations, and placement should be properly done. So what are the steps of placement? We have 3 steps in placement, which is global placement, which takes around 50% of the runtime. So global placement, and this is the initial step where the tool finds an approximate location for the standard cell based on timing and congestion. So placement step is timing driven and congestion driven. The tool is being built accordingly, and the placed cells will overlap with each other, and they will not be present on the power rails So cells will be overlapping with each other because this is just an initial placement step, and this is quite fast and it is accurate for the timing and congestion analysis. So here in this image, you can see that the standard cells are overlapping with each other and they are not placed properly on the standard cell rails. So this is how a global placement will look like, which is the initial placement. But this will not be visible to us because when we set the command for placement, the tool will process these steps subsequently. But the tool will generate a log file. So each log file will have information on global placement, the next step, and this subsequent step. So at the end of global placement, what is the congestion level and how many cells are placed? All these details will be available in the log file. So the second step is legalization. The tool moves the cells to legal locations. So in this step, the cells are aligned on the routing track and all the overlaps are fixed. So this is like more or less the final step of placement. And next is detailed placement. This is a step where minor modifications takes place in the movement of standard cells. So we have 3 steps in placement, which is global placement, legalization, and detailed placement. Next is placement bounds. This constraint controls the placement of a group of standard cells. For example, if we find that there is a group of logic communicating with a particular macro, but when we do placement, the tool places the group of logics in a spread out way. In that case, there will be longer routes and which will lead to more delay during timing analysis. So in that case, when we know that this particular group has to be placed together, we have certain scripts to and commands to place to group these cells into a group name. So say group A, and then we do the grouping first and then we perform placement, so that the tool will place these cells at a particular area, and so that they are placed closer to the macro, which will help for less delay during timing analysis. And we need to add spare cells in the design. So what is the need for spare cell in a design? These spare cells are actually part of the standard cell library, and they are dummy cells which are inserted in the netlist. So they do not perform any function. Then why are they required? For example, if we are currently working on iPhone 10 and we have completed the design process, 2 years later, the customer comes back to us and says that I want to design iPhone 12. So for this, I just need to add 2 more features to the iPhone 10 database. So this is the request, and they have given us the clear information that they want to add 2 new features to the iPhone 10 database without removing any old features present in iPhone 10. So for this reason, the front-end team takes the request, they modify the netlist accordingly, and they give you the new netlist with the 2 new added features. The 2 new added features may be addition of an AND gate or some other function. So in your Innovus database, you will have some cells in your iPhone 10 database known as spare cells. So they will be present in each design. So when the customer comes back to you with this request, you remove the 2 spare cells and you add these 2 new cells. So that is why we need spare cells in the design. In case we don't have spare cells in the design, we will not be able to take the request of iPhone 12. So that is why these spare cells are like very important in the design. And right now, lots of cross checks are being done during the physical design cycle to make sure that these spare cells are present from the beginning till the end of the design phase, so that they can accommodate future functional engineering change orders after the tape out of the chip. So here you have an image showing the good placement and bad placement. So at the end of good placement, you see that your pins are spread out through the chip, and you have different logics, standard cells properly placed, and you see the fly lines, the connections are neat. Whereas in bad placement, the pins are in a cluster at one end of the chip, and you have you see the placement of standard cells is not good, and the connections are a mess. So this is the difference between good placement and bad placement. There is decrease in area and length of wires when your placement is good, whereas in bad placement, there is increase in area. Also there is easier routability in a good placement, whereas routing is difficult in bad placement. Shorter wires are present in good placement, leading to low power dissipation. Longer wires are present in bad placement, leading to high dynamic power dissipation. You have less hotspots, resulting in maximum performance, and more hotspots in bad placement, so that your performance is degrading. Next step is congestion. Congestion is a very important aspect to be taken care of in physical design. So congestion occurs if your number of available routing resources is less than the required routing resources. A congestion map can help us to visualize the quality of placement. And soon after each step in physical design, when you open up the Innoverse graphic user interface, you will be able to see the congestion map. So what are the reasons for congestion? So these reasons are based on a theory. So high standard cell density at one particular location, creating hotspots. If there is a cluster of cells at one particular location, no proper placement blockages. If there is less routing resources, placement of macros in center of the chip instead of the boundary. So all this will create congestion. And how do we fix them? We can identify areas with low utilization and modify the floor plan accordingly, so that the standard cells are evenly spread throughout, and spread out the top level ports or move to other sites. Increase of spacing between macros, add proper blockages and halos, and also worst come worst, we can also resize the block to reduce overall congestion. But this is our last step, because when you resize the block, you have to go through the full physical design process. So this is the end of placement, where you have standard cells being placed in the center of the chip. The next step is clock tree synthesis. Clock tree synthesis is the fourth step in physical design. So why is clock tree synthesis required, and the need for clock tree synthesis? We have one clock source and we have lots of flip-flops in the design. So for example, this clock source communicates with this flip-flop and the distance is quite short, whereas this clock source communicating with the last flip-flop, the distance is quite long. So there is a difference in delay. The delay between this clock source and the flip-flop is short, whereas the delay between this clock source and this flip-flop is quite long. So this will create problems for the tool when it tries to fix hold time in the physical design phase. So in order to make things easier, the tool adds clock buffers and clock inverters in this long path. So when the tool adds clock buffers and clock inverters in the long path, it will reduce the delay between this clock source and this flip-flop. So when the delay is reduced, it is the delay between this clock source and flip-flop is quite balanced with the delay between this clock and this flip-flop. So almost all the delays are quite balanced and delays are minimum in the design. So when the delay is minimum, it is easier for the tool to fix timing. That is the main reason why we use clock tree synthesis in the design. There are some cases where even clock tree synthesis is not required. We can bypass this step and we are able to meet timing. So it depends on the clock frequency, number of clocks, complexity of the design, whether to use clock tree synthesis or not. So what are the objectives of clock tree synthesis? We have minimum skew, minimum insertion delay, maximum transition, and maximum capacitance. What are the effects of CTS? We have addition of clock buffers and clock inverters in the design, and there is increase in congestion because there is addition of new clock buffers and clock inverters, which is leading to congestion. How is CTS achieved? We achieve CTS by adding clock buffers and clock inverters. We minimize this to minimize the skew, to balance the clocks, and also non-default rules is applied to clock nets. So why clock buffers and clock inverters? Clock inverters are used for clock tree building, clock buffers for clock tree balancing. Clock buffers have equal rise and fall time. Normal buffers do not have equal rise and fall time. So that is the main reason why we use clock buffers and clock inverters for clock tree synthesis. Clock buffers are increased in size than the normal buffers. That is the main reason why after adding clock buffers and clock inverters, there is more area being consumed, and these clock buffers and clock inverters consume more power. So we need to ensure that less number of clock buffers and clock inverters are added in the design. This is achieved by having a good floor plan, proper placement, and so on. So here you have a launch clock and a capture clock. So the launch clock is for a particular register, and capture clock is for a particular register. So if your launch clock and capture clock are closer together, if the two registers are closer, then their skew is less. If they are far apart, then their skew is more. So when their skew is more, you can use combinational logics in between to bring down the delay. So your min delay and max delay is for a basic understanding on the launch clock and the capture clock, and the delay on the rise path is your min delay, and the delay for one clock cycle is your max delay. So earlier we had two concepts like clock tree and clock mesh. So in those days, clock mesh was used for clock tree synthesis. So during this process, the tool will create a mesh kind of structure with all the clock buffers and clock inverters over the entire chip. So this created lots of issues with power consumption. Like even if there is in one particular area, if there is proper balancing of clocks, the tool will still add clock buffers and inverters on it because it is a mesh. So then later this clock tree concept came into effect, where the clock tree clock buffers and inverters are added only for where there is a need for balancing. So in this way, we achieved less power consumption, and we slowly moved from the concept of clock mesh to clock tree. So how do you achieve a proper clock route? We pre-route the clock nets. So this clock tree synthesis is a step before routing. So first priority is given for the clock nets, and we use higher metal layers. For example, if six metal layers are used for physical design, we will use metal 6 for the power routes, and metal 5 will be used for clock tree synthesis. And we also shield the clock nets with viridian ground on either side. This also helps in achieving a proper clock route. Non-default routing rules are added in the design, especially for clock routes. These rules consist of double wide or triple wide metals with double wide spacing. So these rules are used to route clock nets and any other sensitive net in the design. These non-default routing rules are provided to us from the manufacturing organization. And it is specific for each technology node we use. So this is after clock tree synthesis, you can open up the design in Innovus, and there is a command called ccopt clock tree debugger. So when you click this command, your clock tree synthesis will be visible here with all the buffers, clocks, their pattern, their clock structure. And when you click each buffer or inverter, you can find out the name of the buffer, clock buffer inverter being added, and your clock tree structure. You can see that buffers are added in between. Previously, it was one long route from this clock source to the flip-flop, but now you have in buffers in between, inverters in between, to balance the skew and to bring down the delay. So now you see that your clock tree is properly being created, and you can see the skew, min delay, max delay, and so on. The skew group is displayed for you. So this helps for debugging purposes. The next step is routing. So with routing, we complete the design phase in physical design. Routing, we have certain goals for routing: to minimize the total wire length, minimize the critical path delay, minimize congestion hotspots. So the goals of each step are almost the same. And we complete routing without increasing the total area of the design. Routing occurs in 3 orders. First is power routing, which we completed it during the power planning step, where we connect the macro and standard cell power rails. So this was during power route. Second is clock route. The clocks are given higher priority in using the routing resources. So first we have power routes, second we have clock routes, and clock route is done during clock tree synthesis. The third step is the signal route. Signal route occurs during routing step. Signal route is mainly the functional routes. So rest of the nets in the design is routed. The entire routing resources can be used at this stage because we have already completed the routes for power and clock nets. Routing grids are defined for the entire layout, and routing direction is also defined for each metal layer. For example, M1 will be assigned horizontal routing tracks with separate pitch value, and M2 will be assigned vertical routing track. So M1, M3, M5 will follow horizontal routing track. M2, M4, M6 will follow the vertical routing track. So all these routing track will be superimposed on each other. This is the routing pattern to be followed during route step. So here is a snapshot of how a routing track looks like and how a route is created. So horizontal routing track is metal 1, vertical routing track is metal 2, and you have standard cells in the design. Standard cell pins are present. So metal 2 route is created and metal 1 route is in horizontal direction. So between the metal 2 and metal 1 route, you have a via interconnect. So this via interconnect is mainly used to connect metal 2 with metal 1. So if you have a route with metal 2 and metal 1 and you don't have a via interconnect in this connection, the route is present but it is still open. There is no current flowing through this connection because you don't have a VI interconnect. So these VI interconnects will consume more power. So it is always advisable that we should not have more number of metal layer changes in the design. So the more number of metal layer changes, you will have more VI interconnects in the design. So your route has to be perfect, and you need to allow the tool, you need to give space for the tool to create proper routes without lots of metal layer changes. So here you have a metal 1 route, and then you have a metal 2 vertical route. So this is how a simple route structure will look like. There are 3 stages of routing, same as placement, where you have global routing, track assignment, and detailed routing. Global routing is the first initial step where the tool creates traces of routes. So this traces of route is being created, and they are not actual routes. So this routing is based on timing and crosstalk noise. What are the objectives of global routing? To minimize overflow of congestion, reduce total wire length, and runtime reduction. Types of global routing are time driven, as I mentioned earlier, and is crosstalk driven. So wire delays are taken into account, and the tool makes sure that timing is properly met during the route step. And crosstalk driven is where the tool avoids long paths of routes. If, for example, if there are 2 routes running for a long time, and then the tool will create an abstraction and break it into shorter paths. Second step is track assignment. Track assignment is a stage where the routing tracks are assigned for each global routes. So we have horizontal and vertical tracks depending on the metal layers, and also all the overlapped wires will be rerouted, and this is the perfect step. So this is detailed routing, which is same as track assignment, where all the routes are properly created and they are final with no overlaps. So after route step, when you open up the design and the congestion map, you will have an image like this, where congestion at the boundary is blue in color. So there is less congestion. There is minimum congestion in the region here in yellow and green, and here you have some hotspots in red. So these hotspots in red to be fixed and analyzed. Maybe they can be due to some clustering of standard cells on one region, which creates this hotspot. So we need to analyze it. Signal integrity has to be taken care during route step, which is closely associated with crosstalk. So here a switching signal will affect the neighbor net. So for example, if there are 2 nets running parallel, if one net is switching, it will affect the other net. The affected net is the victim, switching net is the aggressor. So how do you prevent crosstalk? We limit the length of parallel nets, we shield the special nets, and we upsize driver or buffer. So this is the end of route step, where you see you have all your routes created. You can see that this green metal layer is metal 3, which connects the first standard cell with the last standard cell, and you have some empty spaces left in between. So we need to ensure that there are no empty space in the design. So if you have empty spaces in the design, it will lead to latch-up violations. So how do you fix this empty space? All the empty spaces after route step should be filled with cells known as filler cells. So they are added after routing optimization. The filler cells do not perform any function, but they are just present for the power rail connectivity and to fill up the gaps between the standard cells. So they only contain N-well, P-well, and the power rails. So after adding filler cells, you see that the design is complete, and there are no empty space in the design. Now we go into the physical verification and timing analysis. So in physical design, static timing analysis plays a very major role to fix setup and hold time. So in each company, there will be a specific engineer known as STA engineer who takes care of the timing constraints, generation of timing constraints, fixing timing issues in all the projects. So what is STA? Static timing analysis is one of the techniques used to verify the timing of a digital design. So it makes sure that our design meets timing constraints, and STA only checks timing and not functionality of the circuit. So we check for setup time and hold time. So what is setup time? Setup time is the minimum amount of time the data signal should be held steady before the clock's active edge, so that the data are reliably sampled by the clock. Hold time is the minimum amount of time the data signal should be held steady after the clock's active edge. So I will show you a snapshot in the next slide. Here you have a clock path and you have a data path. So data can toggle in the region, but it has to be steady before the clock's active edge for setup time, and it has to be steady after the clock's active edge for hold time, and it can toggle after the region. So this is the setup and hold window. So what is required time and arrival time? So we will go through some basic definitions of static timing analysis, so it will help you to understand how is the STA being implemented in the physical design flow. So we have a required time and arrival time. Required time is the time required for data to arrive at a certain point. Arrival time is the time at which data arrives at a certain point. So you have a slack here is the difference between the required time and arrival time of a signal. Positive slack indicates the design is meeting timing. Negative slack indicates the design is not meeting timing. So if your design is not meeting timing, then you need to add buffers or remove buffers, upsize buffers, and so on to fix this timing violation. You have a setup slack where your required time minus arrival time, and you have a hold slack where your arrival time minus required time gives your hold slack. You need to understand a concept called clock latency, which is your source latency plus your network latency. So here you have a PLL and a clock source. So this delay is the source latency, and from clock definition point to the final register is your network latency. So you have lots of logics in between. So all this gives you the network latency, and the combination of source and network latency is your clock source. Next is your clock skew. It is the difference in arrival time of the capture edge of two adjacent registers. So positive skew is where you capture clock comes late than the launch clock, because that is the basic flow where your launch clock comes earlier and your capture clock is late. So you have a positive skew. But when you have your launch clock coming late than the capture clock, it results in negative skew. So your timing path consists of 3 elements. So all your timing reports will have a start point, combination logic in between, and end point. Start point is start of a timing path where the data is launched by the clock edge. Start point also consists of clock, primary input port, sequential pin with input delay. Combination logic contains AND, OR, XOR elements in between. So flip-flops, registers, and latches are not included in the combination logic. So endpoint is the end of the timing path where data is captured by the clock's edge. There are 4 kinds of timing paths. We have input port to register, register to register. So this is your input port to register, register to register, register to output port, and input port to output port. So input port to output port, input port to register is controlled by this combinational logic, and register to register is controlled by this combinational logic. So if you place these 2 registers together, then there will be less logic required and the delay will be less. If your 2 registers are far apart, then the delay is more and you will require more logics in between. And this is your register to output port. So all these depend on how your placement is done, how your floor planning is done, and how well is your clock tree synthesis. So how do you fix setup violations in the design? We upsize the cell from A2 to A4. We insert buffers to fix setup violation, and we can increase delay in the clock. And to fix hold violations, we add delay, we detour the routes, we downsize the cell, so on to fix hold violations. This is how a timing report will look like, where you have start point at top and followed by end point, and then you have path group which is iClock and path type which is max. So you see that you have a data arrival time and a data required time, and the positive slack is where your data required time is greater than your arrival time. So this meets timing and we don't have to fix it. Next is a timing report where you have an end point, a begin point, and your required time is phase shift minus setup plus the other end arrival time, and arrival time is obtained through all the flops. So you have a positive slack here. And here you check for hold. You have required time equals other end arrival time plus hold plus phase shift minus cycle adjustment, and your slack is your arrival time minus required time. So with this, we complete the timing analysis phase of physical design. And this is the last step, which is the physical verification. So physical verification is we have design rule checks, layout versus schematic, and we also have electrical rule check, XOR check, and the logic equivalence check. So design rule check is DRC is a process where the physical database is checked against design rules. These design rules are provided by the manufacturers to the design engineers. So DRC should be clean before the chip is passed to the foundry. So types of DRCs are minimum width of metal layer, shorts, spacing between metal layers, minimum area, and so on. Shorts, for example, here you have a short caused by the same metal layer in horizontal and vertical direction. Spacing violations, because of this metal piece here, there is spacing violation between these 2 metal layers of same layer. So this causes a spacing violation. The basic DRC checks in physical design are width of the metal layer, spacing between metal layers, and VI enclosure. Second step is layout versus schematic check, where we check for LVS, the schematic versus the layout, to check, make sure that they both are the same. So extracted netlist is from the GDS, source netlist is from the schematic. So extracted netlist and source netlist, when we compare them, we get this LVS report, and we need to ensure that there is no short, no opens in this LVS report. Types of LVS errors are shorts, opens, etc. So you see here there is a open, a short between two same metal layers. Electrical rule check is the methodology used to check the design against electronic rules like floating gates, shorts between source and drain, floating interconnects, etc. XOR check is to compare the original and modified database. This is done to make sure that only the required modifications have been made and no other modifications have been done by accident. So this check will generate a report which has all the mismatching geometries in both the layouts. Logical equivalence check is the last check. Here, design passes through different steps like place and route, sign off, ECOs in IC design. But after each step, the functions should remain the same, because you cannot have a different function in front end side and a different function in back end side. So here you have an initial RTL, and the RTL gets modified. They check whether it is logically equivalent. RDL modified, RDL is synthesized for gate level netlist, and we check whether it is synthesized correctly. And this is a synthesized gate level netlist is pushed through CTS, repeaters are being added, place and route is being performed, and we get the place and route netlist. So we need to ensure that the function in this RTL stage and the function in this place and route stage should be the same. The last step is power analysis, and we will end with this. This is mainly to ensure that chip consumes less power and the proper power connections are being done. So what are the components? We check for dynamic or switching power and static or leakage power. So your total power in the chip is your switching power plus short circuit power plus the leakage power. Dynamic power is the sum of switching and short circuit power. So total power includes static power plus the dynamic power. And switching power is dissipated when the internal and net capacitance are charged, discharged. Short circuit power is power dissipated by a short circuit connection between VDD and ground. Leakage power is nothing but static power, which is power consumed while the circuit is inactive at zero state. So how do you reduce dynamic power? We reduce the switching activity, the toggle rate. We can also select cells during floor plan, during physical design, which consume the less dynamic power and reduce supply voltage. IR drop is power supply in the chip, which is distributed uniformly through VDD and VSS metal layers. So when voltage is applied to a metal wire in the design, current starts to flow through these layers, and some voltage is dropped because of the resistance of metal wires. So this causes IR drop. Types of IR drop analysis are static IR drop analysis and dynamic IR drop analysis. So static IR drop analysis calculates voltage drop of entire chip with no activity. Dynamic IR drop is calculation of voltage drop of entire chip with worse switching activities. So how do you reduce IR drop? We can add extra power stripes in the certain regions, and also we can add decap cells. These are decoupling capacitors which are spread across the region with high switching activity to maintain the voltage. So we can add additional power rails as seen here in blue, so that this will strengthen the VDD and ground power. And we can add decap cells. So these decap cells are present in the region, and whenever there is a drop in voltage, these decap cells will discharge current and to make up the loss. So methods to reduce IR drop are PG connection, make sure that all the power pins of macros, IPs are properly connected. Now the power switches numbers can be increased. And there is a new method known as cell padding to space out the cells which switch simultaneously. So they help to reduce the peak current demand at one particular region. For example, here if you see that the cells are placed close to each other, but here they are spread out. So when they are spread out, it is when there is a peak current demand, high switching activity, when all the cells are switching together, there will be the activity is spread out in this region, which results in less power consumption. So reasons for poor power grid, which is disconnected instances, when your VDD and ground pins are not properly connected to your main power stripes from macros, or there are shorts, there are any missing vias. Like I mentioned before, there is a connection between metal 2 to metal 1, but there is a via in between which creates this connection. If this via is missing, then it is an open. So all this results in poor power grid. So how do you strengthen the power grid? We can add incremental addition of vias to drop from higher metal layers to lower layers, add wider PG stripes to improve the current conductivity. And electromigration is also another check to make sure the power is properly dissipated, and EM is only worse at higher temperatures. So when you fix, make sure that all your VDD and ground pins are properly connected, there won't be any EM violations. So to fix EM violations, we increase the width of the wire, and also we have shorter wire length. So each step of physical design is interconnected. So we need to ensure that each step of physical design is done with utmost care. And this is your IR drop map, where you see you have more hotspots in this region. The red is with more hotspot, and you need to go back to your Innovus database to see, is there any missing via or missing instance connections, or missing VDD connections or VSS connections in this region. Okay, so before we conclude today's talk, I would like to give you some information about life in VLSI. There are lots of online certification courses available in India and abroad. So you can register in those courses, and they give you some hands-on also, especially on static timing analysis, floor planning, clock tree synthesis, and so on. So you have in-depth study on each step of physical design. And then you have internships, studies available in India in IITs, NITs, BITS, some top universities who offer research opportunities, VLSI research labs, and there are lots of research being going on. So you can contact the professors directly through email, and you can put up your interest in this field, your certifications and so on. So if there is any opportunity as research assistant to be a part of their project, so it will give you some hands-on and some on the job training, which will help you in future. And studies internships available abroad are in NTU Singapore, NUS Singapore, NTU TEM program in Singapore, and some universities in UK, US. Some job roles in the semiconductor industry are design engineer roles, verification engineer, application engineer, manufacturing engineer. So under design engineer, we have lots of opportunities for front end, back end, FPGA, DFT, analog mixed signal, RF, IP design. And for verification roles, we have front end verification, EDA tools validation, etc. And application engineer roles for corporate application, field application. Corporate application are those engineers who conduct business meetings to promote the EDA tools like Cadence, Synopsys, Graphics. Field application engineers, they work closely with the design houses to fix issues, bugs. And manufacturing engineer are engineers who work on the fabrication plant, the foundries like foundry, fab managers, tech support guys, clean room specialists, etc. Some major recruiters in the field of VLSI are ST Microelectronics, MediaTek, Infineon, TSMC, NVIDIA, Intel, Qualcomm, Xilinx, NXP, Broadcom, and Cypress Semiconductors, Micron. So all these companies have their headquarters in either US, in Taiwan, Europe side, and they also have their design houses in South India and North India. ST Microelectronics has a very big design center in Noida, and it is the second largest design house in the world for ST Microelectronics. And the last three companies at bottom, Cadence, Mentographics, Synopsys, are the EDA tool companies. So they design, they come up with the tool, namely Innovus or ICC2, to perform this physical design flow or the front-end design flow. So they work closely with the companies at top. They join hands with them. These design houses buy the tools, and lots of interactions, business interactions, technology updates go on between these two companies, and that is how these chips are being developed in the market. So with this, I would like to conclude my talk for today. And for further queries, or you have any doubts, you can email me, or you can also connect me through LinkedIn. Once again, thanks to all the students, faculty members, researchers for taking your time today to be part of this session. And also thank KCG College of Technology, the department head, and Dr. Deepa Jose ma'am for arranging this talk and for giving me this opportunity to be part of this session. Thank you.
Thank you, sir. That was a very informative session. Over to Deepa ma'am for further proceedings.
Thank you so much. It was a very informative and very detailed session related to power planning and placement routing. And in fact, you also explained about the various job roles available and regarding the various companies also, which our students can try. I hope these students and faculty will get motivated to work in this specific domain of VLSI. And let us go to the question answer session now. So any students or faculty have any questions, they can unmute and they can ask the questions to sir. Yes, Lokesh, you have a doubt?
Yes, am I audible, ma'am?
Yes.
Okay. Sir, in manufacturing the semiconductor chips, China is the leading country. But why India can't manufacture semiconductor chips?
Okay, the main problem we have is lack of infrastructure, because countries like Europe, US, even Singapore, they have lots of fabs for manufacturing, because mainly is one is power supply, and the next is the lack of manufacturing facilities available. But right now, I think Indian government is taking more efforts to set up fabs in India. So I think in due course, we will have all the companies coming up with fabrication plants, which will create more job opportunities in the field of manufacturing sector.
Okay, sir. Thank you, sir. Sir, another question is, since it's a pandemic situation, can you suggest some methodology to learn for the core field like VLSI or embedded system like this?
So for this one, you can, as I mentioned earlier, yes, lots of universities in India and abroad, they also have started online courses with VLSI. So this actually is a good initiative, and lots of webinars have been taking place across the globe in VLSI. So this will actually help you to gain more knowledge in this pandemic situation.
Okay, sir. Thank you, sir. Sir, finally, is your company providing any internship for UG students?
This one actually in Singapore, we are linked to only the local universities in Singapore. So in India, maybe you can write to the HR of ST Noida, because they do offer internships.
Okay, sir. Thank you, sir.
Yeah.
Anyone else?
Yes, ma'am. This is Hemavati from ECE, ma'am.
Okay.
Can I ask my question?
Yes, yes. Yes.
Okay, sir. What are the skills required to become an expert in VLSI physical design, sir?
Okay, to be an expert in VLSI physical design, you need to have good scripting knowledge. So as a fresher, you need to have good understanding of Perl, Tcl scripting, and also the basics of physical design. And usage of the tools comes only by experience. So once you start using this tool, because the same tool has been used for generations, Innovus from Cadence, or ICC2 from Synopsys. So now this tool doesn't change. Like for in the field of information technology, you have to update with lots of skills and tools, but this one, it only comes by experience, because you keep using the same tool for generations. So as a fresher, we need to make sure that we have good understanding of the concepts, logic behind digital design, and we need to be good in Perl and Tcl scripting.
Okay, sir. My next question was, is it mandatory for second-year students to acquire the extra skills by doing internships, sir?
It depends on which field you are planning to pursue your career. If it is in electronics, if you want to be in the core field, then you can start attending paper presentations, symposiums. So this will give you some idea, because you will have your students presenting some new concepts for you. So by that you can gain more knowledge.
Okay, okay, sir. Thank you, sir.
Okay.
Sir, there's a question in the chat box. Can I read it out?
Yes, ma'am.
So in power planning, why we have ground ring outside only and power ring inside? It's one doubt.
Okay. In block power ring structure, we have always this ground ring outside and VDD ring inside. So this actually is we don't have any specific purpose on this. So it differs by each engineer on how to place the block power ring. So some engineers place ground outside, some engineers place VDD outside. But the main concept is we need to ensure that the macros are being covered by block ring and ground ring, and power ring, and we need to ensure that there is proper spacing between the ground ring and power rings. So there is no mandatory rule that ground ring should be placed outside, power ring should be placed inside, and so on.
Thank you, sir. So there's another doubt posted by one of the faculty members. Sir, can you share insight on how VLSI can be linked to AI and the data science?
Yeah, VLSI to AI is right now there is more focus on AI in India and abroad, and also there are lots of VLSI enabled chips coming up in the design field, like Intel and all. They already started working to generate AI enabled chips. So this is how the future will be, like moving from VLSI to VLSI and AI working closely together to come up with this AI enabled chips. Because the reason is when we work closely with AI, VLSI AI enabled chips, they work more accurate, and their processing time is faster than the normal VLSI chips. So research is already being done, and right now NVIDIA and Intel started working on AI enabled chips.
So will it be like a hardware software co-design sort of design, or it will be
Yes, it will be a hardware and
Okay.
software coded design. So we will first
Okay,
generate this,
co-design, okay.
design the chip, and then the algorithm will be fed into it.
Okay, sir. So I think one last question, but it is a general question. Why our government is not establishing a semiconductor manufacturing unit in India?
Yeah, so right now I saw some news that Indian government is planning for establishing manufacturing units. The main reason we have a problem is because of lack of logistics right now, because manufacturing unit needs current 24/7 and also the required infrastructure. So this is been into discussion, and so we have lots of design houses in India, but we don't have a proper manufacturing unit. So lots of industries are working towards it now.
Yes, sir. Thank you, sir. Any other doubts or queries by anyone?
So there is a question: which language is used in physical design? We use Perl and Tcl scripting for physical design in the field, but there is no specific language used. We only use this tool called Innovus. So you can use the latest scripting languages for physical design. So any scripting languages is okay. It's up to you.
So will there be online courses in the websites that you have provided for these languages, sir?
Like in YouTube and social media, we have lots of commands.
So students can
yeah,
study.
there are lots of handbooks are available for these, and there are lots of simple programs, so they can develop from that.
Okay. Yeah. So I think all have cleared their doubts. So thanks once again from the faculty of KCG and from the management of KCG College of Technology for sharing your expertise with the participants and students from across various states across India. Thanks once again for your time, and your lecture was very detailed. It covered like whatever we had heard in bits and pieces. You took very much in depth and in very detail. Thanks once again, sir, for the talk.
Thank you, ma'am, for the opportunity, and wishing you the very best to all the students. Thank you, ma'am. Have a good day.
Thanks.
Thank you.
Yes, thank you, sir. Over to the participants.